In this week's lab, we will be isolating caffeine from coffee. Caffeine is a white crystalline powder. It occurs naturally in many plants. Some examples are coffee beans and tea leaves. Caffeine stimulates the central nervous system. And shown on the right here are some examples of beverages that contain different amounts of caffeine. A 12-ounce can of cola can contain 30 to 40 milligrams of caffeine. 8 ounces of green or black tea can contain 30 to 50 milligrams of caffeine. 8 ounces of coffee can contain 80 to 100 milligrams of caffeine. And an 8-ounce energy drink can contain 40 to 250 milligrams of caffeine. Caffeine is an alkaloid, which is a class of naturally occurring organic compounds that contain basic nitrogen atoms, like what is shown here. Caffeine is a xanthine, which is a family of naturally occurring organic compounds that have been found to stimulate the central nervous system. On the bottom right, 3 examples of xanthines are shown. Theobromine is found in cocoa. Caffeine is found in various plants, such as coffee beans and tea leaves, and theophylline is found in tea. Caffeine can be extracted from coffee beans to isolate pure caffeine or make decaffeinated coffee. Different extraction methods include direct contact, which uses an organic solvent, usually methylene chloride. Next is the water process, which uses hot water and steam, followed by filtration through an activated charcoal filter. And the final is the carbon dioxide process, which uses carbon dioxide at a high temperature and pressure. A problem with extracting caffeine from coffee beans is that caffeine is accompanied by other substances such as cellulose and tannins. Cellulose is the structural component of plant cells. Cellulose is separated from caffeine by adding hot water, since cellulose is insoluble in water and caffeine is soluble in water. So we take our coffee beans, add our hot water, the cellulose is left behind in the solid phase, and the aqueous phase contains the caffeine and tannins. Tannins are phenolic compounds, meaning they contain aromatic rings with one or more hydroxyl groups, like what is shown here. And they have molecular weights between 500 and 3000. And here is an example of tannic acid. Tannins in coffee are broken down into 2 classes: hydrolyzable, meaning that they react with water, and non-hydrolyzable, meaning that they do not react with water. Hydrolyzable tannins in coffee can form free gallic acid when they are hydrolyzed. Non-hydrolyzable tannins in coffee are polymers of catechin. These tannins are acidic, and when they react with calcium carbonate, which is a base, they are converted to their calcium salts, which are highly soluble in water. So for example, 2 molecules of gallic acid can react with the base calcium carbonate to form the calcium salt by deprotonating this carboxylic acid group. Now that we've produced the tannin salts that are very soluble in the aqueous layer, we can add methylene chloride to extract the caffeine from the aqueous layer. Caffeine is more soluble in methylene chloride than water, so the caffeine will move to the organic layer, which is down here, and the tannin salts will then stay in the aqueous layer. To summarize the extraction of caffeine from coffee beans, we first add hot water to the coffee beans to separate the cellulose from the caffeine, leaving the cellulose in the solid phase and the caffeine and tannins in the aqueous phase. Then calcium carbonate is added to produce the tannin salts, and methylene chloride is also added. Methylene chloride is also known as dichloromethane, which is abbreviated as DCM. This then separates the tannin salts, which stay in the aqueous phase, from the caffeine, which goes into the organic phase. Now for a summarized procedure. Step 1. Make coffee with 20 grams of coffee grounds and 250 milliliters of water in an espresso maker. The TA will do this part for you. Step 2. Add coffee to a 400 milliliter beaker with 6 grams of calcium carbonate. Step 3. Heat the beaker to 70 degrees Celsius for 10 minutes. Step 4. Allow the mixture to cool so that it's warm enough for you to touch with your hand. Then filter with a fitted funnel with a C-Light filter aid. To prepare the C-Light filter, you need to assemble this apparatus, which consists of a fritted glass funnel, which is shown up top here, a flask that connects to the fritted glass funnel, as well as a hose that connects to the vacuum line in your fume hood. Next, you mix the C-Light with water in a beaker to form a slurry. You then add the slurry into the funnel and wait for the water to drain, leaving a C-Light cake, which is shown here. You then discard the water filtrate, then you can filter your coffee through this apparatus. The purpose of this C-Light filter aid is that the C-Light filter cake can filter finer particles than the glass for the loan, and this only works when you're collecting the filtrate, not the solid. Step 5. Use liquid-liquid extraction to separate the caffeine from the tannin salts. Liquid-liquid extraction is a technique that is used to separate compounds based on their solubilities in two immiscible solvents. Remembering the phrase like dissolves like, in this case, the tannin salts are more soluble in the polar solvent, which is the aqueous layer, and the caffeine is more soluble in the less polar solvent, DCM. And DCM and water are both immiscible, so this makes it easy to separate the caffeine from the tannin salts. If you're ever wondering which layer is the organic layer and which is the aqueous layer, you need to look up the densities of both of the liquids, and in this case, water has a lower density than DCM, so that means it sits on top of the DCM. To do the liquid-liquid extraction, split the coffee filtrate into 2 equal fractions in 2 different separatory funnels. Next, extract with 20 milliliters of dichloromethane 2 times. To do this, you add your DCM to the coffee filtrate in your separatory funnel. Always when you're adding liquids to the separatory funnel, make sure that the stopcock is closed. You can make sure that it is closed by making sure these handles are perpendicular to the stem of the separatory funnel. Then cap the top of the separatory funnel and roll and vent. You want to roll the separatory funnel and not shake it, because shaking will cause an emulsion to form, which will cause it to be hard to separate your 2 immiscible layers. By venting it, you want to hold the separatory funnel like is shown in this picture here and open the stopcock to relieve the pressure that builds up in the separatory funnel. Always when you're venting the separatory funnel, make sure that you are pointing the stem into the fume hood to not spray any of your lab partners or anything else around the room. Next, place the separatory funnel in a ring stand and wait for it to separate. Once it has separated, you can drain the organic layer and collect it in a beaker, leaving the aqueous layer still in the separatory funnel. You then repeat this process once more, combining both of the organic layers in a beaker. Step 6. Dry the combined organic layers by adding magnesium sulfate. This is a drying agent which removes any of the leftover water that may be in your organic layer. Drying agents are usually inorganic salts that form hydrates by combining with water. For example, magnesium sulfate can combine with up to 7 molecules of water. When you add your drying agent to your organic layers, you will see it start to clump up. This means that it is absorbing water. When you add more drying agent, you'll see it clump up more but make smaller clumps. And then once you've added enough of your drying agent, you will see free floating crystals throughout your organic solution. Step 7. Use vacuum filtration to remove the magnesium sulfate. Vacuum filtration is a technique that is used to separate solids from liquids. In your case, you will be separating the magnesium sulfate from the DCM. To set up this apparatus, take the filter flask that is in your drawer and hook it up to the vacuum source in your fume hood. You then take your Buchner funnel, which is the large white funnel you have, stick it inside of a rubber garment and stick that inside of the top of the filter flask. You then place a piece of filter paper inside of the Buchner funnel, then turn on the vacuum source. You can then pour your solution of magnesium sulfate and DCM through the flask, and then you can take the filtrate and transfer that to a 250 milliliter round bottom flask. Step 8. Evaporate the solvent using the rotary evaporator. A rotary evaporator is commonly used in organic chemistry labs to evaporate low boiling point solvents. Here is an image of the rotary evaporator that are in our labs. To use this, you hook your round bottom flask containing your compound and your low boiling point solvent to the bump trap right here. You then put the system under vacuum, which lowers the boiling point of the solvent. The round bottom flask is then heated by the water bath, which evaporates the solvent, causing the solvent to travel up through the rotovap to the water-cooled condenser, which condenses the evaporated solvent, causing it to drip down, and the solvent is collected in the collection flask, leaving your compound behind in your round bottom flask. Here's how to use the rotary evaporator. Turn on the water bath using the temperature control. Turn on the vacuum and turn on the water to the condenser. Connect your round bottom flask to the bump trap using the yellow cat clamp that you have in your drawers. Close the air bleed tap to put the system under vacuum. Turn on rotation using the rotation speed control knob. The purpose of rotation in rotary evaporation is to reduce the probability of bumping and foaming in your flask. Lower the round bottom flask into the water bath. Wait for your solvent to evaporate. You will see your solvent start to collect on the water-cooled condenser and drip down into the collection flask. You will know when you are done with your evaporation once all of the solvent has evaporated from your flask and all you see is solid caffeine left in your round bottom flask. Then, once all the solvent is evaporated, you can just do the opposite process. Lift the round bottom flask out of the water bath, turn off the rotation, open the air bleed tap, remove your round bottom flask, turn off the water bath, vacuum, and water to the condenser. Now you have crude caffeine that needs to be purified. Step 9. Use recrystallization to purify the crude caffeine. Recrystallization is a purification technique that works by dissolving a compound and impurities in a hot solvent, then cooling the solvent, causing the compound to precipitate as crystals that can be separated from the solvent. Sometimes you can recrystallize your compound using only one solvent, but that is not the case for caffeine. You need a mixed solvent system of acetone and petroleum ether. Here is acetone and here is petroleum ether. Don't be fooled by its name, it is actually not an ether, and it is a mixture of alkanes, usually pentanes and hexanes. For this experiment, we have chosen the solvent system for you, but this is something you'd usually need to find out on your own. For a mixed solvent system, the first solvent, acetone in this case, is a solvent that your compound should be soluble in. The second solvent, petroleum ether in this case, is a solvent that your compound should be insoluble in. Acetone is a polar molecule because of this oxygen atom. Similarly, caffeine is a somewhat polar molecule because it contains various atoms such as oxygen and nitrogen. This allows caffeine to be soluble in acetone. Petroleum ether is a hydrocarbon and is a nonpolar molecule, so caffeine is less soluble in petroleum ether. To carry out your recrystallization, add the minimum amount of hot acetone to caffeine to make all of the caffeine dissolve. Then add petroleum ether dropwise to your solution until it becomes cloudy. Then cool the flask in an ice bath and wait for crystals to form. If crystals do not form, you can take a glass stir rod and dip it in the solution, pull it out, and let the solution dry on the tip of the glass stir rod. Once the glass stir rod is dry, you can stick it back into the flask. Crystals should then form. If this does not work, you can take that glass stir rod and rub it on the inside of the flask, right here, right at the top of the liquid. This should form crystals in your flask. Step 10. Filter the solid using the Hirsch funnel, and this is the vacuum filtration system that I showed to you before. The only difference is that we're using a Hirsch funnel this time, which is the smaller white one that you have in your drawer. Step 11. Calculate the percent of caffeine that you isolated from your ground coffee. You can do this using the fact that 1 gram of coffee contains about 13.5 milligrams of caffeine. So then you could say 13.5 milligrams of caffeine per 1 gram of coffee multiplied by 20 grams of coffee, since that's how much was used in this experiment, to find that the possible amount of caffeine that you could extract from all of this coffee is 270 milligrams of caffeine. Then you take the amount of caffeine that you actually isolated right here and then divide that by the 270 milligrams of caffeine. Multiply that by 100% and that gets you the percent of caffeine that was isolated. So, for example, say I isolated 95 milligrams of caffeine from 20 grams of coffee grounds. I would take 95 milligrams of caffeine, divide that by 270 milligrams of caffeine, multiply by 100%, and that gives me 35%. And remember sig figs, so there's 2 sig figs here. That's because we used 20 grams of ground coffee and also that I isolated 95 milligrams of caffeine. Step 12. Determine the melting point of your caffeine. Melting points are used in organic chemistry to characterize organic compounds and determine a substance's purity. The presence of impurities lower the melting point and broaden the melting point range. To determine the melting point of your sample, you first need to pack a melting point tube. To do this, you need to place some of your caffeine sample onto a watch glass. Then take the open end of the melting point tube and press it onto the sample, causing some of the caffeine to go into the melting point tube. Then flip the melting point tube over and drop it on the lab bench a couple of times, causing the caffeine to pack into the closed end of the melting point tube. When finished, your melting point tube should look something like this, with about 1 to 2 millimeters of packed solid. You can then insert your melting point tube into the melting point apparatus and look at it through the eyepiece. You can then turn on the heating controls, and you want to slowly approach the melting point of caffeine. You should know the melting point of caffeine because you wrote it in your pre-lab. When determining the melting point of caffeine, you want to record a melting point range. The melting point range is when you see the first drop of liquid form when the caffeine starts to melt to when all of your sample has been converted to liquid. And this will conclude the lab.